2,000 years, libraries have been the most successful way of storing information. But think of the space. The information is stored in an organised way. We take it for granted that we can find anything. It's just a question of how long it takes. Not long if you use one of these. You probably couldn't even carry 100 books. But here, instant access to 2,000 books on a single disc. And it certainly cuts down on bookshelves. But why do we want to store information? And how can we do it? One alternative is to remember everything, but there are limits to human memory. From cave paintings to computers, people have invented many ways of storing information. Some have been around for a long time, like writing and pictures. Here they're being used to put together a film about the history of sound recording, starting with the inventor Thomas Edison. But making TV uses other, newer forms of stored information. Visual information can be stored magnetically on videotapes. The script and instructions to control the machinery are stored on computer discs. And all the sounds, voices and music needed to finish the programme on tape, compact disc and cassette. Different types of information stored and retrieved by different systems. Let's see what they've put together.
Stop.
Time was when everyone wanted a big record collection. With the rise of the personal stereo, cassettes took over, tougher and smaller. But now young people are dancing to a new format. Compact discs rule the high street record shops. Why have they been so successful? Because the quality of recording is so much better, or so we're told. Better sound, more reliable, almost indestructible. The older ways of storing sound just can't compete. This graph shows how quickly it's happened. In 1986, the first CD players appeared. Records and cassettes had almost equal sales. In just a few short years, the CD has overtaken vinyl. Very interesting, but this isn't just a new product, it's a whole new science. Do you know the difference between recording on a record and on a compact disc? So what's wrong with the long-playing record? Let's start at the beginning. Well, it all started with Edison, the first person to record sound. This is one of the first Edison phonographs. From these early machines to the latest turntable, all gramophone discs are a mechanical way of storing information. What does that mean, you might ask? The original sounds were recorded onto a master cylinder made of wax. The energy of the sound waves was transmitted to a needle. It vibrated up and down, cutting a groove in the cylinder as it rotated. Copies of the original were made, like this one. The sound information is retrieved by running another needle along the up and down movements on the floor of the groove. They called it heel and dowel recording. The needles were very heavy, the wax was fairly soft. Now can you see why it was abandoned? Eventually the floor of the groove was worn flat. The sound was rubbed out. On a modern record, the sound information is recorded as side-to-side movement rather than up and down. Think about the pressure between needle and record. You can see it's an improvement. But not everybody looks after their records. There are still some, thank you, some problems with mechanical recording. What kind of machine is there which can retrieve information without damaging it?
Yep. So we'll have some of that.
On audio tape like this, you can record any kind of... Sorry, can you cut that bit out? On audio tape like this, you can record any kind of information. The tape can be cut and edited together. There's nothing to touch and nothing to see. Makes you wonder how it works. Well, the tape itself is just a simple plastic film. Strong, but not that interesting. But on both video and audio tape, it has a coating of either iron or chrome compounds. That should give you a clue. What do you know about iron and chrome? Not much to see on a blank tape, but this disc contains a suspension of magnetic particles. You know how iron filings respond to a magnet? Well, it's the same but much finer. Put the disc over a tape that's been recorded on, and we get a pattern. The pattern must be produced by some kind of magnetic field. So how did it get there? First, let's record something. The sound is converted into electrical signals. These signals arrive at this part of the machine, the recording head. After passing across the recording head, the tape gives us the stripy pattern. A pattern of electrical signals giving us a pattern of magnetic stripes. What's the connection? Let's take a closer look at the machinery, the head. Most machines have 3 heads, to record, play back and erase the signal. There are 2 elements to the recording head, a coil of wire wrapped around a hoop of metal. The electrical signals representing the sound pass through the coil. What happens when an electrical current flows through the coil? A magnetic field is produced. Bending the metal core concentrates the magnetic field by bringing the opposing poles of this electromagnet closer together. The electrical signals are in the form of alternating current. What effect does that have on the magnetic field? An alternating current produces an alternating magnetic field across the gap. But how is the tape changed by the magnetic field? Just looking at a piece of blank tape doesn't give us much of a clue. But at higher magnification, we can see that the tape coating is made from millions of tiny needle-shaped particles. You've seen how bar magnets, like compasses, move in a magnetic field. Perhaps these particles do the same. Do they change as we record something on the tape? Here's the particles after recording. Doesn't look like they do move. So how does the tape become magnetic? We need much higher magnification and then some imagination. This is the current theory. Within each tiny particle are even smaller areas called domains. Each of these domains acts as a tiny magnet with 2 poles. This tape hasn't been recorded on. The magnetic domains are oriented in different directions. When the particles pass across the recording head, the magnetic field causes the domains to line up in the same direction. Reverse the direction of the magnetic fields and... Before we go on, have a think about this. What difference would it make if the tape was a continuous sheet of metal instead of particles? Right, back to the recording. Imagine that the electrical signal is a simple alternating current. The changing magnetic field lines up the domains first one way, then the other. Of course, in a real recording, the signal is much more complex. So you might be wondering, how do we retrieve the information from the tape? Let's take a look at the playback system. Look familiar? Well, that's because playback is basically similar to the recording process. So similar that some tape recorders, cheap ones, use the one mechanism to do both jobs. We know the magnetic field on the tape varies. That's the pattern of the domains. Any moving magnet passing a coil produces a current. That's called magnetic induction. A changing magnetic field, like the tape, induces a changing electrical current in the coil. Send it away to an amplifier, and there's your information back. Magnetic fields and coils. As long as one moves relative to the other, something will happen. And the erase head. That's pretty easy. The direction of the magnetic domains is jumbled up. How? Because the electrical signal in the coil is designed to produce a random magnetic field on the tape. Back to where we started, so we can record a new signal whenever we want. Something odd about this new camera. Where's the film? It doesn't have one. It has a floppy disk instead. That means the image is stored magnetically. The disk is covered with magnetic particles. Unlike tape, it's a flat surface, but they're both magnetic. So what? Well, for one thing, if you don't like the picture, you can just erase it and record another one. And for another, if something interesting or strange happens, you can instantly replay the picture as soon as you get back to a television. No waiting for the photos to come back from the shots. Magnetic recording is very flexible, but that presents problems. For any method of storing and retrieving information, you have to ask just how long it's going to last. Sometimes the machinery becomes out of date. Have you ever seen a pianola which plays these rolls? Sometimes the material, like early film, deteriorates. Who knows how long modern computer disks will last? Books can take a lot of rough treatment, but how robust is magnetic storage, like tapes and floppy disks? Well, it depends what's around them that might damage them. Apparently not so tough, but how much of a problem is it? We've seen various ways of storing and retrieving information, but let's go back and ask a fundamental question. What is being stored? This pen records the changes in air pressure, which accompany changes in the weather. The marks left by the pen are a continuous record of the air pressure. This way of storing information is called analog recording. The groove of an LP is a good example of an analog recording. It is a continuous model of the actual sound we're hearing. That's what analog means. If someone hits the drum hard, the groove takes a big swing. Let's take a look at what the same recording would look like digitally. Compact discs record sound digitally. The sound at any fraction of a second is represented as one of these 16-digit binary numbers. The numbers are stored as a pattern of pits cut into the surface of the disc. The beginning and end of every pit represents a 1. The spaces in between and in the middle of the pits represent zeros. But there's another advantage. Instead of a needle running over the pits, the information is picked up by shining a laser onto the surface and detecting the light reflected back. No more worn-out grooves. We've become used to turning things into numbers. Digital instruments seem to have replaced dials all over the place. Very space age. Is this just a fashion, or are there advantages? One advantage of numbers is that they're very precise, particularly binary numbers, like those used in digital compact discs. Take a simple example. You want to get into the bank at night. The door is controlled by an electronic lock. Let's go back and look at that again. When you first approach the bank, the door is locked, but sliding the card through the slot unlocks the door by completing the electrical circuit. The circuit has 2 positions. It's either closed, opening the door, or open when the door is shut. We call this a bistable circuit. We can represent it with numbers. Either it's 0, open, or 1, closed. All very interesting, you might say, but so what? Well, these numbers help us to spot mistakes in digital information. Let's take a look how. Remember the analogue recording of air pressure? What could have caused that? It could have been someone banging the instrument. Or it could have been a lost penguin suddenly exploding next to the weather station. Either way, it isn't an accurate recording of the air pressure at that moment. But with an analogue system, you can't tell the difference. And like a click on your favourite record, the correct information is missing forever. Now look at the same changes in air pressure recorded digitally. Digital recording takes measurements at particular times, maybe every quarter of an hour. This is called sampling. Every point can be represented by a number. If the information isn't recorded close enough together, it doesn't look exactly like the analogue trace, and you miss things, like exploding penguins. So let's increase the sampling rate to once every minute. Increasing the sampling rate means we don't miss things that happen quickly. But hang on, now we've got the penguin again. Now here's the clever bit about digital. It's not that there aren't errors, there are, but they can be automatically removed. Let's take a simple case, a tone produced by a tuning fork. We know that the sound wave should be smooth, so this must be a mistake. If it was on a gramophone record, you might hear something like this. But on a CD, the compact disc player has electronic gadgetry which checks the waveform by comparing different regions. If they don't match, it recognises that there is a mistake and replaces it with a number halfway between the points on either side. Damn clever, this digital recording. You can store more information, it's more precise, and it can correct its own mistakes. So, where's the drawback?